Cuando queráis comenzamos.
Thank you, everybody, for coming. It's a great pleasure for me to introduce one of my colleagues and collaborators, Alexandre Zanchet. I'm going to do a brief introduction of his career. Alexandre made the PhD in the University of Rennes in the Institute of Physics. Then he came for a postdoc into the National Research Institution in the Institute of Fundamental Physics, and where he is now a tenure researcher there in the Department of Molecular Astrophysics, where he's devoted his career to the reactivity of systems of astrophysics interest. And he's going to talk about the reactivity of atomic radicals in these seminars. And thank you for accepting the invitation. And everyone, thank you.
Thank you, Christina, for the introduction, and also thank you for the invitation. So, hello, everybody. Today I will talk to you about reactivity of atomic radicals and let you give an overview of how I usually deal with this kind of problems. So the free radicals are species with unpaired electrons, for those who don't know, and this gives them a special characteristic in comparison with closed shell species, because they have typically an enhanced reactivity, because electrons don't like to be alone, so they will always try to catch another electron, making bonds or something like that. They have a different spin momentum different of zero, so that means that they have also magnetic properties, and that makes also that usually the reactivity of this kind of species may occur on several electronic states at the same time. So radicals are generated in general by fragmentation of closed shell molecules. It can be fragmentation due to UV radiation, electric discharge. Also, very high temperatures can break bonds and produce radicals. And radicals will be quite relevant in several fields of the chemistry, in particular in gas phase chemistry. For example, in combustion, the radicals will be the responsibles of the propagation of the chain reaction. So the chain reaction can be controlled or uncontrolled. And so you can have controlled fire, uncontrolled fire, controlled explosion, uncontrolled explosion. So, and all this is due to the reactivity of radicals. Also, they are quite relevant in atmospheric chemistry on Earth, but also on Titan or other exoplanets, because in atmosphere you have always UV radiation, you can have lightning, so you have electric discharge, this will generate radicals, this will trigger chemistry, very complex in general. And so, well, radicals are really important there too. And also, they are kind of important in astrochemistry, because in the interstellar medium, a lot of objects, or the majority of the objects, are in the gas phase, and the reactivity is usually triggered by radicals or ions, in particular in very cold region, like intermolecular cloud. But then also they play different roles in the several steps or phase of the matter, no? Because the chemistry in a cloud will be different than in the protostar or the formation of a solar system or a planetary system. You will always have a different chemistry, and so in function of the physical condition of the medium, you will have reactivity. But in all the case, radicals will have an important role. But radicals are also important not only in gas phase, but also it is known that they are very toxic for biological system, because, for example, the OH radical is very reactive with DNA and can damage DNA. So there are also this part of reactivity in liquid phase. But well, this I won't about this theme today. So the thing is, for all the previous fields I've shown you, people studying, for example, combustion or atmospheric chemistry in general, try to make chemical models of the possible, of all the network of chemical reaction possible that can happen there, for example, in atmosphere or in interstellar cloud, or even, for example, to optimize an engine of a car to reduce pollution. So they need to make some modeling and simulation, and for that, they require the rate constant of every fundamental step to kind of use a master equation of kinetics and see how will be the evolution of the different species. And so that's why it's important to study the individual reaction of each possible reaction of all possible radicals with all possible molecules. So that's a lot of work. You can imagine. So the problem is that studying this kind of reaction is kind of complicated and challenging because to do an experiment on this kind of species, since they are very reactive, it's very hard to have a controlled production of a radical, concrete radical, and study a concrete reaction. It's also very complicated to control quantum state in an experiment. And also, if you generate too much radicals, they will react between them. And so you cannot measure the reaction you want. But for theory also is a challenge because typically there are multi-reference systems. You have to take in account several electronic states, often coupling, and so that's a mess always. And so, well, that's why it's kind of challenging, but also important. So I give you some example of experiment where they can study the reactivity of radicals. For example, there is the cross molecular beams. So it's a very nice experiment because you have two molecular beams, and so you can collide any species you want. The problem is that this kind of experiment only give you relative cross section. So you cannot extract a rate constant from this kind of experiment, but still they give a lot of information. Then you have another kind of experiment, which is the Crésu style experiment. So this is a gas expansion where the chemistry occurs. So this is very powerful because it can give you rate constant directly. But the problem is that you cannot treat radical reaction in this kind of experiment because they are so much reactive and the pressure is relatively high. And so you can only study reactivity between radicals and neutrals. Also, you have other kind of experiment with better control when ions are involved because with ion you can use octupoles and quadrupoles and stuff like that to capture and guide the ion. So, and furthermore, this kind of experiment can provide absolute cross section. So with an absolute cross section, you can recover the rate constant. But the problem is that you can only apply this when you have ions, and there are a lot of neutral radical reactions that have to be studied. So for all these reactions that you can study experimentally, you have to rely on theory. And so typically the strategy to treat this kind of problems is to use the Schrödinger, try to resolve the Schrödinger equation the more accurately possible. This is done using the Born-Oppenheimer approximation. Basically, is electrons are so fast compared to the nuclei that any movement, any motion of the nuclei, the electrons will readapt instantaneously. And so you can say that the nuclei will move in the potential generated by the electrons. So that's the idea somehow. So to do that, the first step is first for a given position of your nuclei, resolve the electronic structure of the system. So for that, you resolve the electronic Hamiltonian. And if you do that for several possible positions of the nuclei, what you can get and obtain is the global potential energy surface of the system. So that means that the potential that will guide the motion of nuclei. Just to give you an idea, or to those who are not familiar to what is a potential, this would be a representation of the gravitational potential of the solar system. No? So you see that, for example, Jupiter is much more massive, so you have a deep well of potential. And for example, if you are on Jupiter and you want to go to Saturn, you need a lot of energy to escape the gravity of Jupiter, overcome a barrier, and then you can reach Saturn. So conceptually, it's very similar for a chemical reaction. You have a potential, but not from gravity, but from electrostatic forces. But the idea is the same. When you have a potential, you have to overcome a barrier to go from one point of the potential to another one. So to give you some idea on that. And well, once you have, you know your potential, then what you can do is to study the dynamic. So this is done by resolving the nuclear part of the Schrödinger equation with the term of electrons, including the potential. And with reaction dynamics, you can study a lot of things. Inelastic collision, reactive collision, and you can obtain cross-section, different class cross-section, gravitational distribution of products, and for all of this, you can also get the rate constant. So this is very useful. The thing is to do the thing the best as we can. What we are doing also, not only we consider electrons by quantum mechanics, but also nuclei. So basically what it means is that we consider all the nuclei as waves. Your potential will be like a scattering object, no? And when you have a wave reaching a scattering object, then you see where the wave is scattered. And so the scattering of the wave will give you information of the product that you have. So basically, it's another formalism, but in the end, it's similar that if you throw, for example, a lot of trajectory considering particles, covering an ensemble of possible initial conditions. The advantage is with a wave, you have everything in one step, but the calculations are much more expensive. So now that I give you more or less the methodology what we apply, I will now give you an example of the two system reaction of astrophysical interest that I have studied, and I will present the result to you now. And basically, this will be two atom-diatom reaction of oxygen and sulfur cation with molecular hydrogen. These two reactions are quite relevant in the interstellar medium, and in particular in what they call photodissociation region. Photodissociation regions are basically the edge of the molecular cloud. No? Imagine there you have a very massive star emitting a lot of UV photons. So these photons are very energetic, so they will ionize everything they find. Since in interstellar medium you have a lot of hydrogen, basically what you will do, you will ionize all the hydrogen atoms. But at some points, there are so much hydrogen atom that you have absorbed all the UV radiation above 13.6 electron volts. When this occurs, you enter in a region where you can have neutral atoms, and at some points when the UV radiation is absorbed enough, you can start to form a stable molecule because they are shielded by the edge of the cloud. And so inside the cloud, it's completely dark. You have no light because everything is absorbed. And the photodissociation region is basically the frontier between the ionized gas and the rich molecular clouds. So what's the particularity of atomic radicals? Well, basically what you have, all know the S and P orbitals, no? So when you have an atomic radical, what you will do is to fill these orbitals, depending on the number of electrons you have, you can get this different situation. For example, carbon, you have two electrons, nitrogen 3, oxygen 2 again. And so for oxygen, for example, if you have this kind of configuration, Well, actually, you have these orbitals are strictly equivalent. So if you see how you can distribute all these 4 electrons in 3 orbitals, you realize that you can have 3 equivalence arrangements. So that means that basically you will have 3 electronic states that generate in the oxygen atom. For sulfur cation, you have 3 electrons, single electrons in 3 orbitals. So there is only 1 configuration in this case, but it's a quartet state, so very high speed. So H2, well, H2 is a closure molecule, so nothing to comment about. But what about the possible product you expect if you react an atom with H2? Well, it's to form the hybrid. If you form the hybrid, basically what you will obtain is that the p theta orbital will make a bond with the s orbital of hydrogen. Then you have the py and px orbitals are orthogonal, so you will have a non-bonding orbital, well, 2 non-bonding orbitals, and then again you fill with the number of electrons you have, and you see that for OH radical, for example, you have 1 electron that can be or in p by x or in py. So again, you have a doubly degenerate state, polar p state. In the case of sulfur, it's simpler somehow because you have only 1 configuration, which is a sigma state, but again, it's high speed. We'll see later what are the implications of that. So what happens when you have now your atom, your 3 configurations of the atom, which are completely degenerate when the atom is alone, but when it will meet H2, well, of course, if the electrons are not in the same orbital, the interaction with H2 will be different. So each of these configurations will lead to a different electronic state of the system H2O. So basically, you will trigger a reaction if you want to study oxygen plus H2 that will occur on 3 states. It can start on any of these 3 states. Okay, now for the product, kind of similar. You have your hydrate, so with with an electron that can be in the 2 non-bonding orbital, and the interaction with the hydrogen atom will also be different. So in the product, also you will have degenerated states. So if you try to do the correlation diagram, then you see that in the case O plus H2, to get OH plus H, you have 2 potential energy surfaces that will lead from reactive to product. And in collinear configuration, these 2 states are completely degenerate. And so the saddle point is the same for the 2 potential. So that's a peculiarity of this system. However, if you consider the geometry of the saddle point and you try to study the potential as a function of the bending angle, you see that one of the 2 surfaces has a potential increasing slower with the bending angle than the other one. So this, when you will have a dynamics, it means that if you have a potential which will be more open, it will be easier for the chemical reaction to go through this point, and so you will have more reactivity. And that's what you find if you study the cross section. You see that the cross section of the A double prime state is larger than the one of the A prime state. But if you want to get the real reactivity of the system, you have to consider the average of the 2, because it's quantum mechanics. You can start on one or on the other, but in the end, you will have an average. Basically, that's what you have to do. Study the reactivity on one surface, on the other, then making the average. Here I show you some results on the cross-section. So you see that will be the cross-section that occur on the A prime potential energy surface, and you see that the cross-section is somewhat lower than the one you obtain in the A double prime. Now, combining the two cross section doing the average, then you can extract the rate constant of the reaction. And this is what we found. And we compare it with experimental value that were measured a long time ago. This reaction is kind of important also for combustion and a lot of other systems. And you see that really you can reproduce fairly well the rate constant of this reaction. And as you can see, we reproduce it on 8 order of magnitude, because here we are 10 to the minus 18, 10 to the minus 10. So I mean, our calculations are really, really accurate for this kind of stuff. Now, what is the additional interest that we may have in photodissociation regions that I showed you before? Well, actually, the UV radiation is so high that you can pump the vibrational level of hydrogen. And so, as you can imagine, if you have a hydrogen with a lot of vibrational energy, it will be more reactive than hydrogen which is not vibrating very much, because each quantum vibration is half electron volt for H2, and you can populate up to V equal 10. So that's really a lot of energy. And this affects the dynamic. And this we can do the simulation to see what is the impact. And here I show you the rate constants for several vibrational level of H2, and you see how the reactivity increase. If you have 4 or 5 quantum vibration in H2, even at very low temperature, you have a very fast reaction. So that's kind of interesting for the interstellar medium, where the temperature are kind of low. But not only that, because if you have vibration in your H2, this will also reflect in the vibrational distribution of the OH you produce by the reaction. And this can be observed. This can be observed by astronomers. Because when you have a reaction that is occurring in the interstellar medium, well, actually what the astronomers are detecting are radio frequencies. The rotational transition of molecules emits in microwave or radio frequency. And so basically, the astronomers can detect the spectroscopy of these molecules. And with that, they can infer the temperature of the medium. An example of this is, for example, this is a recent image of JWST. You can see that the resolution of this is amazing. And you can spot that there are several stars which are giving birth there in this big interstellar cloud. And they could capture here a protostar or a protostellar disk, which is basically the formation of the solar system. Now, it's when the part of the cloud collapsed, a star is starting to form. This generate a lot of heat in the medium, and this kind of event now it can be observed with JWST. So following the spectroscopy of OH radical in this object, what the astronomer found is that if you consider only the thermal reaction with of O plus H2, you cannot reproduce or understand the emission you detect. However, if you consider that there is a certain UV flux provided by the star which is forming, and this UV flux will affect the reaction of O plus H2 to produce OH in a certain given state, well, if they take this in account, they could match fairly well the observation. So it means that really the state-to-state chemistry is very important for astronomers to help to interpret the observation they do. Okay, so now I will switch to the other reaction, S plus plus H2. So in this case, it seems in a first approximation, easier because you have only one state that correlates reactants in the ground state, which is quartet, and the product. So this reaction is also endothermic, and same as for the O plus H2, it can be greatly enhanced with H2 vibrationally excited, because with 2 quantum vibration, you start to get exothermic. But well, I won't speak about vibrationally excited in this case. I'm more interested in an old experimental result where they showed several years ago that this reaction is maybe more complex than we may think at the first glance, because you have indeed one contribution of that direct reaction which is occurring on the quartet state, but there is also a shoulder there in the cross section. And at this time, people who made the experiment thought, oh, this is probably a contribution due to intersystem crossing. Because in this case, you see that your quartet state has to cross a doublet state, which can form a very stable complex, H2S plus, and which correlates to the same product. So you can somehow have 2 mechanisms, a direct mechanism, or you stay on the quartet potential energy surface, but you can have intersystem crossing. You switch to the doublet state, and then you end the reaction there. And so we will try to see if we can reproduce that theoretically, this model derived from the experiment. So to that, we have to consider also spin-orbit couplings. So basically, spin-orbit couplings is because in principle, transition between doublet and quartet should be forbidden. But the thing is that electrons are so fast that there are some relativistic effects that makes that somehow a small coupling appears between the states. And this small coupling allows a tiny probability to have a switch of spin state. So, well, there is a lot of selection rule when you want to consider this, so it's a little bit complicated, but basically what you see is that if you want to do the thing properly, you have to consider 2 kinds of family due to the different projections of the spin-orbit states. And basically you have 2 kinds of couplings, one to the associated to the 3 alpha projection and the other to the 1 alpha projection. So again, you have to treat the reaction this time with coupled state, and you have to repeat the calculation 2 times, 1 for each coupling. And then again, you have to do the average to get the final result. So this is what we found for D2 plus S plus. And you see that if you consider 1 coupling, you seem to match more or less the experiment. But if you use the other, which is slower, you don't. And the average, well, okay, you see a shoulder, but much shorter than the one they measured experimentally. So you say, okay, it seems that indeed there is intersystem crossing there, but apparently there is something more. And if you look at the correlation diagram again, you see that there is another electronic state, excited electronic state of H2S plus, also doublet, but which is also crossing the quartet because it has a quite stable well, more stable than the reactant. The thing is that this state, in principle, correlates to a higher electronic state of the product, so it shouldn't contribute. However, if you look in details your spin-orbit matrix, you see that there is also spin-orbit coupling between these 2 doublet states. So it's kind of strange because when you usually hear intersystem crossing or spin-orbit, you always imagine that this will be between spins, different spin states. Well, in this case, in the case of doublets, you have spin-orbit couplings between doublet states. So that was unexpected for me, but it's quite interesting results. So if you consider this, well, it's more complicated because this is the matrix you have to deal with. So it's very, very, well, you cannot do the calculation with a matrix of this size. So what we did is to make another approximation where these couplings which were very low, we say, okay, these coupling are 0. So this allows to simplify somehow this matrix and to get something more similar to the previous one, and you can reduce the problem to three states matrices. So if you do the calculation considering that, this is what you find. A very, very, very good agreement with the experiment on the cross section. And I mean that the cross section of this reaction is really slow, 0.4 angstrom square. And so that is how we can compare with the experiment. And well, okay, maybe you will say it's kind of luck. Well, let's see if we do the same with HD. You see that with HD, also we can reproduce the experiment. But not only that, but we reproduce the huge difference of propensity between the two products, because by changing H2 or D2 to HD, you break the symmetry of the system and the two channels are not equivalent anymore. We can reproduce that. It's a very good agreement with the experiment. And also with H2, the same. This is the calculation in red and the experimental value in blue. So you see that really we are able to reproduce that, and that allowed us to have some kind of new insight of how intersystem crossing works. So now with this, I finish. This will be the conclusion. Reactivity of radicals, as you saw, you could see, generally involves coupling between several electrolytic states, and sometimes coupling are very important to take in account. Also, we can, at least for atom-the-atom reaction, have a very, very good accuracy. We can be predictive because once you can reproduce perfectly an experiment, that means that your simulation is also probably good in extreme conditions that cannot be measured. And also, it gives you a lot of information of the mechanism of reaction and this kind of stuff. And so, well, would be the enlightenment for Express plus H2. I work on this with Octavio Roncero, Niazi Bulut, Mankana Bulut, and also the experimental group of Christian Alcaraz and also Peter Armentwood. And for the O plus H2 reaction, well, with the group of Complutense, Javier Ruiz, Rohan Brina, Marta Menendez, and Sela, and also with some astronomers working in my group in CSI, Javier Goicoechea and Marcelino Lagun. And, well, thank you for your attention. Wasn't too long?
No. So, now we start our process. Please.
Was very clear. So.
No, I can ask. Well, there's something just for when you showed the big batteries of the Zanchet system. Yeah, well, either that one or the next one. Can you show the next one? The next slide.
This one.
So you could make the calculations with the 3 coupled states.
Yes.
Why did you say that you couldn't do it with a larger matrix?
Because with this, we are at the limit of the memory we can access. With 3, we are reaching the top of the memory of the calculus center.
But I do a system with 36 states. How cannot you do like?
No, but because the thing is, you have to consider these 3 states, but also the energy up to where you want to converge the calculation. And so since you have to do calculation for all j's up to 120.
I would do it in a different way. I would do each j separate. Okay.
Yeah, no, but each j is done separately. But the memory you require
For the projection
the
and
RAM memory is so huge that they didn't give it to you.
Oh, okay.
And so with this, we are reaching the limit
Okay.
of what they can give you. I mean, this is 256 gigabytes of RAM. Well, probably there are centers with
No.
more resources, but I don't have access.
No, it's in the way that I do that, I separate it from them in different ways, because you include all the omega projections of J in every J that you have.
Yes, exactly.
Yeah,
That's what makes
How would
the.
you reach omega? So I will parallelize in a different way.
But this is parallelized already.
Yeah, no,
But
but
still, it was too so big that, and so the big one, I mean, it's you cannot. Or you can, but you have to reduce a lot the number of helicity, and then your result is converged completely. But this, I mean, we could manage to, and well, apparently it was good because the agreement with experiment is good. So,
would you treat it if you would find any other resource like a high performance sensor that you found? Could you?
Maybe, but the thing is, since with this model it works, I mean.
Well, no, it worked very well. Yeah, that's true. That's true.
That means that it was a good approximation to cancel this case. Because the problem of these small elements of coupling is that they could combine the two spin-orbit family somehow, but else you can treat separately. So that's why. So the problem is that you can start there and then there if you use the full matrix. But it's not so relevant for the reaction.
It's very clear you talk.
Okay.
Just thank Alex again